Hello, welcome to another module in this massive open online course. So, we are looking at estimation in the context of OFDM or orthogonal frequency division multiplexing based systems, and we have already seen the theory of basically how what is the system model for an OFDM system, and basically how to carry out channel estimation, that is estimation of the various channel coefficients and the subcarriers as well as the channel taps in the time domain in an OFDM system, alright. So, now let us look at a simple example to understand this better. So, what we are going to do in this module or starting in this module is basically look at a step by step implementation of an OFDM system as well as channel estimation. So, let us look at an example . Example of an OFDM system, and in particular what we want to look at is channel estimation in OFDM systems, alright. So, as we have been saying, let us consider an n equal to 4 subcarrier system. So, similar to what we have seen in the previous modules, consider an n equal to 4 subcarrier system, and therefore, we have 4 symbols that are loaded onto the subcarriers, 4 pilot symbols. So, let these pilot symbols denoted by capital X be capital X0 equals 1 plus j, capital X1 equals 1 minus j, capital X2 equals 1 plus 2j, capital X3 equals 2 minus j. These are the 4 symbols, these are the n equal to 4 symbols loaded onto the subcarriers. These are the n equal to 4 symbols which are loaded onto the 4 subcarriers, correct. So, we have capital X0, capital X1, capital X2, capital X3, which are the 4 symbols loaded onto the 4 subcarriers. And now we want to generate the samples in the time domain, and remember, the samples in the time domain are generated by the n equal to 4 point IFFT. So, the samples which are denoted by, so the time domain samples, let me write it clearly, this is the time domain are generated by n equal to 4 point IDFT, that is basically these samples are denoted by X0, X1, X2, X3, and these are basically your time domain samples which are generated by the 4 point IFFT. And therefore, Xk, which is the kth sample, what is Xk? Xk is the kth sample, and this is equal to 1 over n summation L equal to 0 to n minus 1 XL e raised to j 2 pi KL divided by n, which is equal to 1 over 4 L is equal to 0 to 3 XL e raised to j 2 pi KL, alright, KL divided by 4, which is in turn, just simplifying this as far as possible, this is L equal to 0 to 3 XL e raised to j pi by 2 KL. Okay. So, this is basically your xk. So, this is basically your xk, this is the kth subcarrier. This is of course x, capital XL is the symbol that is loaded onto the lth subcarrier, and the time domain samples are basically given by the IDFT of the symbols loaded onto the subcarriers. So, we have the symbols loaded onto the subcarriers. Let us now find what the corresponding time domain transmitted samples are. Okay. So, x of 0, let us start with sample x of 0, that is sample corresponding to time index 0, that is 1 over 4 summation L equal to 0 to 3 XL e raised to j pi by 2 k. For k I have to substitute 0 because I am considering the sample at k equal to 0, 0 times L, which is basically now this quantity is basically 1. So, this is 1 over 4 simply summation L equal to 0 to 3 of XL. Okay. Now, therefore, x0, your x0 is 1 over, it is basically 1 over 4 capital X0 plus capital X1 plus capital X2 plus capital X3, which is equal to, what is this equal to, 1 over 4. Now, substitute for capital X0, which is 1 plus j, plus capital X1, which we have said is 1 minus j, plus capital X2 plus 1 plus 2j, plus capital X3, which is 2 minus j. Remember, we have already given the values of capital A, that is the symbols. These are the symbols that are loaded onto the subcarrier. So, I am simply substituting them over here. So, I have 1 over 4, 1 plus j plus 1 minus j plus 1 plus 2j plus 2 minus j, which is equal to 1 plus 4 into 5 plus j, which is equal to 5 by 4 plus 1 over 4 times j. This is the complex symbol, this is the x small x 0, that is the sample transmitted at time 0. Similarly, let us compute small x1, which is the sample transmitted at time 1. Okay. So, again it goes without saying that small x1 corresponds to k equal to 1, that is the sample corresponding to your time instant 1, L equal to 0 to 3 XL e power j pi by 2, instead of k I substitute 1 times L, which is basically 1 over 4 summation L equal to 0 to 3 XL e power j pi by 2 L, which is now, if I substitute the symbols loaded onto the subcarriers, I have x1 equals 1 over 4 times x0 plus x1 into e power j pi by 2 plus x2 e power j pi plus x3 e power j 3 pi by 2, which is equal to basically your 1 over 4 times 1 plus j plus 1 minus j into j plus 1 plus 2j into minus 1 plus 2 minus j into minus j, and what is this equal to? This is equal to your 1 over 4 plus 1 plus j plus j plus 1 minus 1 minus 2j minus 2j minus 1, and this is equal to basically, let us write this down, this is x of 1, which is equal to 1 over 4. You can see there is basically a 1 minus 1 which goes 1 minus 1 which goes. So, all I am left with is j j minus 2 j. So, this is basically minus 2 j divided by 4 equals minus half times j. Okay. Again, you can check all these calculations, please do them yourself and try to check these calculations. So, we have calculated the sample x1, small x1 corresponding to k equal to 1 as minus half j. Okay. Now, let us compute small x2. Small x2 equals, well, 1 over 4 L equal to 0 to 3 capital XL e power j pi by 2, substitute k equal to 2, 2 times L, of course, the 2's go away, and what we have is 1 over 4 L equal to 0 to 3 capital XL e power j pi L, that is small x2. Now, substituting, of course, the capital XLs which are the symbols loaded onto the subcarriers, I have 1 over 4 x0 plus x1 e power j pi plus x2 e power j 2 pi plus x3 e power j 3 pi, which is equal to 1 over 4. Again, hoping that I am making no mistakes, this is 1 plus j plus 1 minus j times minus 1 e power j pi is minus 1 plus 1 plus 2 j into e power j 2 pi is 1 plus 2 minus j into minus 1, and what is this? This is therefore equal to 1 over 4 1 plus j minus 1 plus j plus 1 plus 2 j minus 2 plus j, and this is basically, if I am correct again, we have 1 minus 1, that is 0. So, basically I have 1, what is this? This is basically equal to, well, I have over here I have a 1 minus 2. So, this is minus 1 over 4, and I have well, basically I have 2j plus 2j plus j, that is 5j. So, plus 5 by 4 divided by j, and this is in fact your x2, that is sample corresponding to k equal to sample for k equal to 2. This is the sample corresponding to k equal to 2, and similarly I think we can do the sample small x3 corresponding to k equal to 3, just to be a little bit more explicit to illustrate how to compute these things, although I am sure that all of you can do this simple 4-point IFFT yourself, just to explicitly illustrate the process. So, this is x of 3 equals 1 over 4, again summation L equal to 0 to 3 XL e power j pi by 2 3 times L, which is 1 over 4 summation L equal to 0 to 3 XL e power j, well, 3 pi by 2 times L. And now again, when I substitute the symbols on the subcarriers, that is x3 equals 1 over 4, what do we have? x0 plus x1 into e power j 3 pi by 2 plus x2 into e power j, well, L equal to 2. So, this is 3 pi plus x3 into e power j 9 pi by 2, because L equal to 3, this is equal to 1 over 4 x0 is 1 plus j plus 1 minus j times minus j, that is e power j 3 pi by 2 plus, well, 1 plus 2 j into minus 1 plus 2 minus j into e power j 9 pi by 2, that is j, and when you simplify this, what do you have when you simplify this? So, that is 1 over 4, and once again you can check this 1 over 4, 1 plus j minus j minus 1 minus 1 minus 2j plus 2j plus 1, and what do you have over here? In fact, you have 1 by 4 times 0 plus 0, you can see this is j minus j 1 minus 1 minus 1 plus 1 2j minus 2j. So, this goes. So, what you have is 0, and this is basically your x of 4. So, what you have is basically, let me summarize what you have. You have the transmitted samples in the time domain which are given as x0, x1, x2, x3, and therefore, these samples, now let me write down the values that we have computed, 5 by 4 plus 1 by 4 j comma minus half j comma minus 1 by 4 plus 5 by 4 j comma 0, this is x3. So, what I have done is beneath each time domain sample I have written down the, so these are your time domain samples, these are basically your time beneath each time domain sample I have written the corresponding value of the sample. And now what we do, as we said, right. So, we have generated the sample small x0, small x1, small x2, small x3 as the IFFT of the symbols capital X0, capital X1, capital X2, capital X3, which are loaded onto subcarriers. Now, the next step is of course adding the cyclic prefix, that is I take one sample. I mean, typically it is not one sample, but for this example one sample is enough, where I take the sample from the tail of this block of samples and again repeat it or prefix it at the head. This is known as the cyclic prefix. For instance, here I am going to take this x3, repeat this x3 over here, or in other words take this 0 and repeat this 0 over here. So, this is basically what we said, and I think you should be familiar with this by now. This is basically what we said is the cyclic prefix. So, the block of transmitted samples over the channel with cyclic prefix. So, the block, and this is important to remember what it is, this is block with the cyclic prefix. The block with cyclic prefix is basically your 0, let me just write it down very carefully. This is 0, 5 by 4 plus 1 by 4 j minus half j minus 1 by 4 plus 5 by 4 j comma 0, this is the block of sample. So, now what we are doing is we have added the cyclic prefix to the time domain samples, transmit them over the channel. And remember, the channel that we are considering in particular, that is the channel that we had considered in the example that we have seen for this illustration of this OFDM, is the simple 2-tap channel, which channel taps H0 and H1. So, the channel that we are considering, let me remind you, that is y of k, this is a 2-tap H0 xk plus H1 xk minus 1 plus Vk. Remember, this is our 2-tap channel, 2-tap, in fact ISI channel, inter-symbol interference channel. Okay, this is your 2-tap ISI channel. Okay. And now, once you transmit, these are the samples, remember these xk's, these samples are nothing but what, let me just illustrate it one more time, these xk's are basically, there is nothing but the, these are the time domain samples that you have got after the, this is what you have got after the IFFT of the symbols loaded onto the subcarriers. And therefore, now what we are saying is the action of the channel is one of circular convolution. Because of the cyclic prefix, you have y equals h circularly convolved with x plus the noise, which means now you take the FFT at the receiver. So, basically this is time domain on the top is the time domain, on the bottom is the frequency domain, and in the frequency domain across each subcarrier, remember we have, that is the fundamental equation of OFDM by L equals HL into XL plus VL. This is across subcarrier L, across subcarrier L, across subcarrier L. What are these YLs? These YLs are the symbol pilot output received across the pilot outputs that are received across the subcarrier L. Okay. So, we have capital YL, which is the pilot output received across subcarrier L. Okay. So, what we have done so far is we have considered a simple n equal to 4 subcarrier OFDM system. Okay. We have loaded the symbols like capital X0, capital X1, capital X2, capital X3 to basically on the subcarriers, that is basically performed the IFFT or the IDFT to generate the time domain samples, added the cyclic prefix, and we looked at what happens at the receiver once you take the FFT. Now, in the next module or in the subsequent module, we will look at what is the operations, what are the step by step operations to be performed at the receiver in this simple OFDM example, alright, starting with basically computing the pilot outputs received across each subcarrier and subsequently estimating the channel taps or the channel coefficients in the frequency domain as well as the channel coefficient or the channel taps in the time domain. Okay. So, let us stop this module here and we will continue this in the subsequent module. Thank you.